Um, so today we have another great speaker. Imtiaz Rangwala is going to be talking to us about the science of or atmospheric foundations of climate science. And Imtiaz, as you all have read, we posted this on Blackboard, is a research associate with the Western Water Assessment and the Cooperative Institute for Research in Environmental Sciences at the University of Colorado Boulder. Imtiaz has vast experience in this subject matter, including quite a bit of modeling, quite a bit of local modeling here in high altitude cold climates here right in Gunnison. He employs the use of climate observations and models for understanding and quantifying climate processes, which we have, began to really hit hard over the last couple of weeks. And he has published numerous high-level peer-reviewed research articles in many of these areas. And today, Imtiaz's interests include development and communication of actionable future climate change scenarios for natural resources management, and particularly here in the U.S. Southwest. And so before we welcome Imtiaz, he has also asked me that we should feel completely welcome to ask questions on the fly. And so please, if any of you have any questions, raise your hand and I could watch out and I could go ahead and let Imtiaz know that one of us has a question here in the room. So let's welcome Imtiaz Rangwala.
Well, thank you. That was a kind introduction, and good morning. So I just want to make sure you all can hear me okay. Okay, right. Yeah, because from your side, I'm not quite sure I hear you totally well, so I might have to ask you to speak up at times when you're asking questions. So, so one of the things I do these days, and I physically sit at the NOAA's Earth System Research Lab, and I have all the other affiliation mentioned here. And one of my tasks these days is to integrate climate science into natural resource management, or in broader into decision making. So just bringing the science of climate change and its impacts into planning for our natural resource in the West primarily. Okay, so I'm not going to talk too much about that today. What I'm really going to do is get into more climate change basics, but at the same time, just want to bring out some of the very salient points that many of us are just not aware of, even the experts out there. So I hope I'll be able to communicate some of those points and that they'll get through in a way that you can use it in an effective way going forward. So I'll start with what's the big story of the day, or of the season, as we say. And for those of you who are not reading newspapers often these days, you may have missed this, but 2015 was one of the warmest year ever recorded by our civilization. And I specifically mentioned the instrumental record, but it doesn't go back that far, and that's what we trust the most. So if you look at that record, going back to the late 1800s, what we see is that there's been a warming trend, and it's become much sharper in the last several decades. And 2015 was one of the warmest ever. A few things I would like to take this plot and make a teaching moment out of it. What you see is what we call an anomaly plot. So you might see several other plots that I can show you, and they use the word anomalies, and most of them are basically, these are change or departures from normal, or departure from a long-term average. That's what we call normal. So what's a normal climate? And usually a normal is we take a large period, average it, and say this is kind of a normal climate. And so you can see And that normal can change depending on what period we consider. But that's how we kind of look at trends and change, and we make these anomaly plots. So remember those anomalies. So yes, 2015 was by far the warmest we've seen, and December of 2015 was the warmest month ever recorded by us in that period, in that record. So, and you can see here, and so different agencies that can do these assessments of temperature out there, of climate is changing, and the surface temperature is one of the most important metrics they use. It's easy to measure. It may not be the best metric to look at out there, one can argue, but it's one of the easier ones to measure, and we have most of our measurements are based land surface or the ocean surface temperature, and they corroborate each other. So there's a Japanese agency, this one in the UK, and we have NASA and NOAA does that same thing, and every year they come up with their assessment, and pretty much what you see a lot of regions in across the globe showing this record warming in December. So what was there a big reason behind it? Again, if you're not following the news, you may have missed this, but we had a very big El Nino event in play for last year and a half, and really got into a very severe mode starting last May. So what you see is a phenomenon where the ocean temperature, let's see if I can get my pointer here. Okay, the ocean temperature in the Central and Eastern Pacific shows this anomalous warming, and this is another form of an anomaly plot where you see departures from a long-term average, and in an El Nino event, what you start to see is, that you have this anomalous warming in Central and Eastern Pacific. But what this event also does is it spews a lot of heat from the ocean to the atmosphere and land system. And so whenever we have an El Nino event, a lot of warming is coming out of the ocean and going into the atmosphere and land. And it's a good deal for us in the southwest US because it brings moisture. It has a tendency to bring more moisture. So snowpack is above average in Colorado. Most likely to be a great ski season for all of you if you want to ski in Colorado. So generally it's good, a good cloud buster, phenomena for the western US, southwestern in particular. And it's doing some of that thing this year as well. And it's really one of the biggest El Nino we have seen, one of the 3 big ones. Okay. Just so going to some of the climate basic stuff, let's look at, let's take a broad view and look at what the climate system consists of, the Earth climate system. And this is one rendition of the different components and processes that occurs that are part of the Earth's climate system. And then if you look at all of these things, so again, you see the sun kind of provide most of the energy, almost 99 to 100% of the energy driving climate system. And within the Earth system, all these components interacting to kind of interacting to have a climate that the Earth experiences. Now, if you look at this diagram, and I can put the diagram of the Earth system, you won't see much difference. And what you see is climate system is part of everything that we see as part of the Earth system. So you can look at anywhere from the oceans, to the land, to the soils, to the snow and ice pack, to volcanic activities, to all the biogeochemistry, all form part of the climate system. And so to really model a climate system, you have to include all of these processes and components into your model. And as I later get into our climate models, what I'm going to show you is that our models are becoming increasingly sophisticated and trying to include all of that. But the name of the game is complexity, and it is a complex system. And it comes back to us all the time that this is a very complex system, and when we change something, when we're it, and humans, when they try to change stuff to the climate system, to the earth system, we are dealing with a very complex system. Sometimes we don't really know how the changes come out to be. Okay, so the issue that's relevant to climate change is the greenhouse effect. And I'm going to spend more time on this, and just to make sure you get the basics right here. So once again, most of the energy that is experienced by the Earth's climate system comes from the sun. So almost 99.9% of the energy comes from the sun. Then, when we receive that energy, then the Earth system distributes it in a particular way within our climate system, and so we play with that energy in very different ways. And you see all these arrows kind of pointing to how that energy is relocated, and we experience the climate in that way. And so greenhouse effect is part of that redistribution of energy. So let's look at it. Let's look at some of these areas. How these sort of radiation coming to the planet. Some of it is reflected by the clouds, and some of it gets reflected by our planet. So, and so clouds have very high reflectivity, and when there are no clouds, it reaches the surface. It really depends on the reflectivity of the surface, that how much of that energy reflects back to the planet. So if you have snow and ice, much more reflected back. But if you have a forest, it's much darker surface. Most of the cases work. But that's really kind of one component of the radiative budget that we experience. The other is, again, I'm trying to get my arrow here. Okay. So part of the radiation that gets actually absorbed by our planet and does not get reflected heats up our planet. And anything that has temperature emits radiation. So if your temperature is about 0 degree Kelvin, you'll be emitting radiation black body. And so does the Earth. It's much warmer than that. And the sun, if we had no atmosphere, our temperature would be about 255 Kelvin, and that's about minus 20 Celsius. And and so because of that temperature, we emit radiation, what we call infrared radiation. This is the radiation that we emit. And if we had no atmosphere, all of that radiation would just escape back to the Earth, to space. But only a small portion of it escapes back into space, because a lot of it is captured by our atmosphere. And that radiation a lot of that is sent back to our planet. And that heating that our atmosphere does for us is the greenhouse effect. So it's that infrared radiation that our atmosphere captures and sends back to the planet is the greenhouse effect. Some of that stuff is re-emitted back to the planet, re-emitted back to the space by our atmosphere, but a lot of it is sent back to the planet, which gives us an extra warm, so we are not 33 degrees Celsius colder than what we would be without greenhouse effect. So the greenhouse effect is a good thing for us in general, because it keeps us at a more optimal temperature than it would be without it. And so why are we concerned about it? So before we get into that, let's look at what are the important components of the atmospheric components that contribute to the greenhouse effect. There are many, and primarily it's water vapor in clouds. Water vapor is just water gas in the clouds, which are basically water droplets hanging out in the atmosphere. So they take by far from a large amount of the greenhouse gas and particles. They primarily produce the greenhouse effect. And then you have all these trace gases that we call the greenhouse gases. They're, again, very small amounts, but they're very important. Again, carbon dioxide is as important as 10 to 30% at any given day. It's greenhouse effect. And we have, and so these are just a small list of greenhouse gases I've listed here. But if you look at the news, these are not the gases most of the gases that we are concerned about. So water vapor clouds are not something we are concerned about. And the primary greenhouse gas we are concerned about from the human emissions point of view is CO2, methane, and nitrous oxide. And so why are we not really talking about water vapor and clouds here? And there's a reason to that, and that's what we'll get into shortly. It's the difference between what we call forcing and feedback. And again, it's all about the process I mentioned earlier. It's like, what are the processes in the climate system? Okay, so where's the problem? Why are we concerned about carbon dioxide, methane, nitrous oxide, and all the other gases listed here? Again, they are in very trace amounts, but the main reason we're concerned about these gases is their atmospheric lifetime. So if you put a water vapor in the air, how long do you think it lasts in the air? And you can have any guess, but it does not last for more than a week or two out in the atmosphere. And it is controlled by really the climate of the atmosphere and land system. And so if it's cold enough, it'll become liquid droplet, it'll fall back to the ground. So it's really controlled by the climate itself, and it has a very short lifetime. But it's really these long-living greenhouse gases that once you put it in the atmosphere, they stay forever. And that's the challenge. So if you put carbon dioxide out into the atmosphere, is there for hundreds of years, if not thousands of years. So in the way we said, it doesn't matter how we emit, it's really how much we emit, because once you put it out there, it stays really great. On the right here is, so these gases are listed in kind of the amounts they are there, so the carbon dioxide by far the amounts, and then in the decreasing order, we see some of the CFCs, these are some of the fluorofluorocarbon that's used in refrigerants. So CFCs are banned now, and so, but they'll still stay in the atmosphere for a long time. And then you have the HFCs, the replacement for the CFCs. Although we solved the ozone problem, we created a greenhouse problem. So they are strong greenhouse gases. Out here in this table, you basically see what your greenhouse warming potential is. And this is basically comparing it. So you compare each of the molecule of these gases to carbon dioxide, how much more powerful they are relative to a single molecule of carbon dioxide in the air. So methane is about 20 times more powerful, nitrous oxide 20 times more, and so on. And you use a particular calculation, but it'll essentially do that. But in short, basically, you have very powerful gases, and thank goodness they are in smaller quantities. But they're all adding to the problem. But carbon dioxide is by far our biggest contributor to the additional greenhouse effect that our emissions are causing. Okay, so let's spend some time on what I mean by forcing and feedback. And we'll be getting to some terms now, and the climate scientists love using these terms on the fly. So I just want to make sure you guys get a good sense of what these terms mean. So So this is what I've defined it on the fly myself. Um, what a climate forcing is just any external element, so something that's external to the climate system, that forces change in the energy budget of the climate system. So even though you think that carbon dioxide is part of the Earth's system, it's there in our atmosphere, it's considered external to the atmosphere, external to our climate system. So again, volcanoes are another example. You know, when volcanic eruption happens, they spew all the stuff out in the atmosphere. They put all these sulfur particles out higher in the atmosphere, like radiation out of our atmosphere, cools the planet. So last time when Mount Pinatubo eruption happened, you know, our planet was cooled down by a degree of 2 Celsius. So that was a perturbation to our climate system, which you call it external. That was the first thing. So that's one of the examples, and I'll show you some more examples. Okay. What's a feedback? So feedback is something that responds to forcing. So it's the internal elements of the climate system, the processes, the components that respond to forcing, and do that added forcing. And so they either amplify or dampen the effect of force. And again, I'll show you some examples. So feedback happens because of the forcing, and they either increase the effect of that forcing or decrease it. Some examples, forcing we talked about, one big forcing we're concerned about is the long-lived greenhouse gases we're putting out there. Other screening of the air pollution we're putting out there, that's the aerosols, the volcanoes, solar radiation. And there are some big forcing terms in our climate system. And there are many more feedbacks. I mean, it's like we can fill pages, we can just have many lectures just about what different kind of feedbacks are there in our climate system. And I just listed a few, and I'll give you some examples. So at the end of the day, it's really, when we talk about climate change, it's the interplay of forcing and feedback, what ultimately drives the climate change response. And if it was just forcing, it was just CO2, we might not have been so concerned about climate change. But it's really all, it's the combination of the forcing and the feedback that makes us very concerned. We are concerned that that some of the amplifying feedback will make the forcing response much more bigger, and the models kind of point to that could be the case. Okay, so a couple examples of feedback. This is one of the most famous ones and very easy to explain, and you may all be aware of this. So the snow ice albedo feedback. And this is an example of a positive and amplifying climate feedback. So here, basically, this is kind of a normal condition, and then where you have, you know, this kind of, imagine this is an Arctic ice, sea ice up there, and then under normal condition, you have a good portion of the sea covered by ice and snow, and most of that has very high albedo reflectivity. And so it reflects most of the solar radiation back. For some reason, it's called global warming, we reduce the amount of ice up there. So that's a forcing. We put more CO2, etc. We warm the planet. That extra warming reduced the amount of snow and ice in the Arctic. And so now we have less ice out there sitting and covering the planet, especially the Arctic Sea. And so more of the solar radiation is now absorbed by this much darker waters nearby. And so that, what it does is further warms the water. You see all the red. So that's the feedback that's at play. It is basically the feedback warming the system more than what was warmed by the forcing. And the cumulative effect of feedback and forcing is that, you know, we lose more and more of the ice. So, right, that's an example of a positive feedback. I also included an example of a negative, a dampening climate feedback, and where you when you on the climate system, and it's slightly hypothetical case, although it's very it's physical nature, but it's a little more complex. And so this is an example of a cloud feedback, but clouds are very complex. They have both positive and negative feedback. This is one example of a negative feedback that a cloud can offer. You warm the system, you increase evaporation from the ocean, you increase the cloud cover, and if you have more cloud cover, less solar radiation is coming to the planet, and different siblings. So a trigger that's warming the climate may actually trigger a feedback that ends up cooling it, so dampen that effect. Okay. At this point, I just want to just put it out if there are any questions related to greenhouse effect, feedback, forcing, but get a good idea, different mode here.
Are there any, has there been any like measure of change in like in the Earth's albedo? I mean, I know it's like roughly like 30%, but I mean, is it, how accurate are the measurements, and is there a change, or has there been a change?
Yeah, that's a good question, and I really don't know the answer because globally, I need to look at how the planetary albedo is changing. So we call it the planetary albedo, which is both surface and atmosphere. So there's the clouds changing, or how the surface is changing. Regionally, we know we are seeing very major changes in albedo. So, for example, a lot of glacier and snow ice lost in many places, mountains as well as, and seasonally we're seeing a lot of change in albedo because snow and ice melting earlier in the season or coming late in the season. Also, you know, the boreal forest is marching northward, so it's increasing the albedo that way. So regionally, there is a good evidence that it's changing, but globally on the whole, how much change, of course, I'm not sure. I think the Arctic sea ice loss is the big change in the albedo. So my guess is you might be seeing a decrease in albedo, but we also know that the Antarctic Antarctic sea ice is expanding for other reasons, and so it may reduce that effect. Any other questions?
Can I ask another related question to albedo?
Yeah.
If Greenland melts all the way, do they know, is there an estimate of like what percentage just Greenland emits, or what percentage that has on the effect of albedo?
Oh, on albedo, okay. I almost thought you were asking sea level rise is the bigger problem for Greenland melting. It may cause over 15 meter of sea level rise. With albedo, no, it will be significant, but my guess is not for a long time Greenland albedo would be a concern because the ice out there is almost 2,000 meters thick, and it'll take a long time for that ice to melt, and albedo is not a concern. But if it all melts one day, I think it would have a problem.
Thank you.
Okay, sure. Any other related to greenhouse feedback first thing? Okay. I'll keep moving, but feel free to ask. So I showed you an example of feedback. Let's look at forcing, because that's really get into a climate change issue. And that issue is that we're seeing an increasing trend in the forcing. And here I'm showing you an example of the carbon dioxide measurement in our atmosphere, and very, very meticulously done by this one Charles Keeling out here. And it's all, and this curve I'm showing you is also famously known as the Keeling curve. And these are measurements that Charles Keeling started to do, and he had the foresight that this was the big problem back in the 50s, and he found funds to set this measurement going up on top of Mauna Loa in Hawaii, where you have very pure air. So one thing about these long-lived greenhouse gases, it doesn't matter if you measure it in your backyard or you measure it up on Mauna Loa, you have this very same reading. And so if anything has a very long lifetime, it's also very well mixed in the atmosphere. So that's why there's very homogeneous concentration all over. So you see several things there, and I would skip going into all of that. You see every year there's a cycle to it. It's basically responding to the boreal forest when the tree gets leaves and it loses leaves. That kind of emission shows kind of fluctuation year to year, but you see it's going up. It's going up since we started taking measurements, and then we crossed the major landmark in 2014. In fact, looks like we did it in 2013 when we went about 400 parts per million. And you see we're still coming down. Last year we did come down again below 400 parts per million, and we're going up. We are right now again above it, and very soon will not come below 400 parts per million. And it's not knowing when we'll come back below that number. So that's a major landmark, and that's something we need to be cognizant of. And we were all doing very important things, when that event happened. But that was an important landmark. Okay, so let's take a little long-term view. It's not very long-term. We talk about planet's history, the geological history, but it's kind of a small snapshot of the planetary system, but it's very important for human beings as a civilization, our own civilization. So basically what you're seeing here is this long record coming out of our ice cores. So these are also measurements and very precise measurements that we can do looking at the ice cores and take out the air bubbles and measure how much CO2 in that and thermal bubbles. So, and what we see is when we do that measurement that at least for the last billion years or so, we were tightly locked in this ice cycle. So we had, for the longest, whenever you see low measurements, we had the ice ages. In fact, it was ice age throughout, because as long as we have permanent ice-covered ice sheet on the planet, we are in ice age. But you see, we were tightly bound between 200 and 300 parts per million, approximately, until we came out of it recently, thanks to our emissions and not knowing where we can go. So we have crossed the 400 parts per million threshold, and we can shoot out of this in 100 years, 50 to 100 years, to anywhere close to over 500 parts per million to close to 900. So really, this is what we are doing is, as I told, we are rapidly changing or forcing to a climate system, and it's a very rapid and high perturbation that we can create to our climate system. And so last time when we were right here, down here, that was our last, we call the glacial maximum. We had about 2 mile thick ice cover over Chicago. So just kind of a sense that, just 100 parts per million had kind of a difference. When we were 100 parts per million down in those cycles, we had these very thick ice cover over much of our land. And that's a large response of our climate system to these kind of perturbation. Now, I'm not saying that all of that's caused by CO2, but it's the interplay of forcing and feedback working together. And the last time we think we had 400 parts per million was really going back 3 million years ago, at least, or further back than that. So we are crossing some thresholds here, and we don't exactly know where it'll take us. There's a lag in our climate system, and that's the reason for being cautious that how much we want to emit. So yeah, this is something I want to say. With climate change, we have, as you saw in the previous plot, there are changes all over. Change is not a problem. It's a real problem is the rate of change. And that's what is the concern here, the rate of change. Okay, so we have put all these forcing, add these perturbations to a climate system, and the climate system is responding. Forcing and feedbacks are at play, and they are causing a pattern of change, which we can call trends. And let's look at some of these trends. So this is from the IPCC report recently, and what is showing that whatever different measurements we take, what we find is that the climate system is warming, and it's unequivocally warming. That's what our records show. And so year to year you see fluctuation, but the system is warming. And what you're seeing that every decade is warmer than the previous decade. It's warming everywhere on the globe, warming faster at high latitudes, but it's really warming everywhere. And at very few places you see some cooling trends, as shown here by blue. What's happening in high altitude regions, something like Tennessee, other high altitude regions out in, and we have this a little bit of a black box for us because we have very limited measurements at these high elevations. But the sense is that the high latitudes and the high altitudes have some commonalities between them. And so we expect that high altitude regions are also very sensitive to this climate forcing and maybe showing a large response. And there's some evidence to suggest that's the case. So we are warming the system. Where is most of the warming going? And if you haven't guessed it yet, more than 90% of that added warming is going in our ocean. And primarily because we have more ocean surface out there to take that heat. Also, because ocean are darker surface, they're taking more heat, they reflect less, and they have high specific heat capacity. Water has, and so they hold on to it. And I shouldn't go all day because there's one ocean and many islands on our planet. But you see a smaller portion going in the atmosphere and continent, and much smaller in other components. So yeah, the ocean is taking the brunt of all the added warming, and then how the ocean behaves really affects everybody on the land and in the atmosphere. So, so many scientists can argue that temperature is not the best measure to look at how the planet is warming, and a better measure actually is how the total heat content is changing on the planet. And because it's all about the added heat. And so here you can look at the changes in the heat budget or the energy budget of our planet, and you see again most of the heat going in the ocean, and it's like this is going since the 1960s. You see how rapidly that heat is accumulating in the ocean. And that's a lot of heat, and I should have put a number how many millions of Hiroshima-like bombs are these. I think there are billions of that of heat that we have trapped in our system. Okay, what are some impacts we are seeing? And these are, again, you can call them trends, the trends of the impacts. So one of the most clear evidence is of the receding glaciers across the globe. There are few that are increasing, and there's a physical mechanism for them, but most of them are receding because of this heat, this additional warming to the system, and some remarkable photos out there. I put some here. So this is Kilimanjaro on the right, and some of the glacier. It is melted to a great degree. We are seeing, a rapid rise in sea level, and so, in fact, sea level observed data as shown by this curve here, the yellow curve, orange curve, and red curve here, between measurements, showing pretty rapid rise, and it looks like the observed sea level is rising faster than what our models can predict. Our models can good job with temperature, but not so well with sea level. And so we are missing some of the processes in the models that should reflect it more accurately. So, and so that's a big concern. Another plot that kind of kind of projects a little bit in the future, but what we see that about 10 centimeter increase in sea level already because of the warming, and then we can increase anywhere by 100 to we don't know where. And this could be a very low estimate. So we can do anywhere from 100 centimeters or more end of century. But many scientists would argue this is a very conservative estimate, and there are processes that can be at play that can increase the sea level faster than this projection shown here. Okay, I mentioned sea ice when we talked about it. And what you see here is that we're decreasing that extent every year, the September sea ice area every year. And this is the trend. And some years have been worse than others, but the trend is negative. And again, models are not able to predict this process. We are seeing the trend. So our system is reacting much faster. So sea level rise, the Arctic sea ice loss, much faster than what our models can say. So we have already lost 10 times the size of Texas in terms of sea ice during September. It's a pretty large change. Yet, we see this large change, and we believe that our anthropogenic forcing is part of the problem, but some people still need more evidence out there. Okay, so let's look at some regional trends, and I probably have to go through some of these very quickly because I'd like to have some more questions from you guys. But regionally, also, we are seeing warming. This is for Colorado, and where we see in the mid-1990s, we've gone in a warmer phase. And you see some of the warmers shown here as from the Colorado climate change report. Something similar is happening for Southwest Colorado. This is the change in the freezing level of the atmosphere. So basically, it is the level, and it's in meters here. So 3,000, it's close to 10,000 feet. So this is where the freezing level, this is what the freezing level from year to year is. And so below freezing level, the rain is falling as liquid, precipitation is coming as rain, above freezing level is still solid phase. So that's one way to look at it. But you see, as we increase the freezing level in the future, what the implication is, are we changing to more rain than snow? And that and so that freezing level also, kind of matches the way our temperatures change as the warming is happening. We see some of the first summers in the Southwest Colorado happen in recent times. So 2002, 2012 were very big drought years. There were also 2 years when we had extreme high temperatures. So again, are we creating new extremes that we didn't see previously? And again, there's some evidence to suggest that is the case. Okay, a little bit of future climate projections towards the end here. And as Yogi Berger said, it's tricky. We're talking about future to make predictions. And there's all kind of uncertainty. It's like, how is a future society will grow? How will our emissions look like going in the future? And then all this issue related to our tools, climate models have uncertainty, and then, our regional impacts, etc. There's uncertainty in all these steps, and they add up, basically. Once you start, and they add up. One of the major uncertainty is, what would our emissions look like in the future? And, so we really don't talk about it. We don't start preparing for 2100 right now. Most of our planning is really close to mid or early 21st century. Out here where they don't look that different, but by the late century they start to look very different. So again, we really need to put a plan in place to decide for this future. But that's a big uncertainty even now, where we'll go in terms of there's some hypothetical rendition of what the future emissions look like, and we use these in our models to kind of look at a response. Again, we have these sophisticated climate models out there, and as I talked about the climate system previously, they try to simulate those processes, they divide the planet into large grids and work with all kinds of these physical equations I mentioned, I show here. And we have several modeling centers across the globe. They each put out its best model, and every few years we come and we do a comparison of what these models are saying, and it gets into our IPCC report. So again, these are our primary tools to look into the future, and they've become increasingly sophisticated in the last several decades. And we have large confidence in them for many climate response because of the anthropogenic forcing. So one of the things that help us evaluate is that they can tell us what the climate or climate change would look like with or without this anthropogenic greenhouse forcing. And so here, the pink curve shows where we have the anthropogenic forcing, and the blue shows where we don't have it. This is kind of a temperature change. And basically it shows that, yes, you're changing the temperature in these modeling experiments where we add these forcing and when we don't add this additional forcing, it doesn't change. So kind of we can do these validation experiments. And same thing with the ocean heat pump. That these changes in the forcing really changes aspect of our climate system, especially by increasing thermal response of the climate system. They can also help us say that, okay, depending on what our emissions would look like, so here 2.6 is the low emission scenario, 8.5 is the high emission scenario. Depending on what the emission look like, how the change would look like. And so for low emission, we see low temperature response, and then depending on the higher emissions, we have high temperature response. Same goes with the loss of sea ice. Same goes with acidification of the ocean, so less acidification in a low emission scenario, a very high acidification in a high emission scenario. So really, the models help us quantify this and understand the impacts. So one of the issues with models is we have all kinds of models, and some models are more sensitive, some are less, so they give us different numbers. So for a doubling of greenhouse gas in the atmosphere, they give us the global temperature increase may be anywhere from 1.5 to 4.5 degrees Celsius. And so that's an uncertainty. That's a big uncertainty. So that's coming out of our models, and so something we have to reconcile. So the sensitivity of the models is an important component, and that adds to this uncertainty, and that we need to be aware of. But we can calculate these sensitivity in different ways, looking at paleo records as well, and matching it up. But it's part of thinking about future risk for these uncertainty, and this the climate sensitivity is one example. I will kind of skip this. This was really showing about the project we had in Southwest Colorado, where we are doing planning and really looking at 2035 period, and what we're finding here is like we have all these response from the models and show a large spread in what the future would look like by 2035. This is across the vertical. This is change in temperature. So the warming can be anywhere from 2 degrees to 5 degrees Fahrenheit. So that kind of uncertainty is there. You start seeing at the regional scale from these models, and so we have to, and they kind of point to different risks out of there, and so we have to consider all the spread to plan for the future. And the future, there are multiple futures that are possible, and so part of the challenge is to work across uncertainty. I'll leave you there, and let me know if there are any more questions in the next couple of minutes or so. Thank you.
I was wondering if you could talk a little bit about why Antarctica is kind of on a reverse trend as far as melting.
Yeah, no, that's really to get into the issue of the complexity of the system, and the ice is not increasing because it's cooling. Ice Antarctica is increasing because you have more water, more cold water that is expanding, and is not able to settle down. So mostly what happens is that Antarctica is the big generation of, that region is the biggest generation of what we call the Antarctic bottom water, that very cold, heavy water just settles down and goes to the very bottom water. Now that water is, because of this additional melting to the system and the changes to the thermal structure of the system, that water, the cold water is becoming ice and not settling down, and increasing the sea ice component of the Antarctic system. So it's more related to the flow around the Antarctica that has increased the size of the ice out there. I hope that answers it to some degree, but and that could be a response to the climate warming. So, and at places, you know, that's a thing. We call it climate change is a good term, but really climate disruption. Sometimes it's a disruption to the way things were happening, in the way the flows were, or the changes from season to season. So what are causing change there, and we're seeing these new kind of trends in this.
Imtiaz, I think you had a meeting at 9. Should we cut it there, or do you have time for maybe another 1 or 2 questions?
Yeah, I can take 2 questions.
Okay.
Sure.
I think, yeah, Jake, and then there's another one, maybe Ayudesh.
First off, thank you for speaking with our class. I wanted to ask you what your opinion was on the feasibility of climate engineering as a climate change mitigation tactic.
Yeah, good question. Yeah, whole lecture or more for that. But it's broadly called the geoengineering. It's, I think, become a very notorious term out there. And but there are some components of it, and now they're trying to subcategorize it and into different processes. One of them is managing solar radiation, and that's was kind of where people are more wary of just playing with the climate system. It's like put solar radiation, put some pollutant up in the atmosphere, some sulfur dioxide particles in the atmosphere, and reduce the amount of solar radiation coming in, or putting this giant mirrors up or sails up in the space and deflecting part of the solar radiation to reduce the heat. So, and a lot of experiments are happening to see what kind of effects they can have on the climate system. We know that we have some proxies. So when we have volcanoes, the big volcanoes that put all these particles, it cools down our planet. We know that happens, but also we know that when during those times we put monsoons, on which most of the world was dependent on, most of the tropical world was dependent on, they get affected. So it really affects, it have implications. So that's where I'm more worried about in terms of what if you try to manage the climate in that way. There are winners and losers. We think about the ocean acidification to our solutions. But then on the other side, there are other solutions where can we sequester carbon to kind of draw down carbon dioxide from the atmosphere. And there could be some great solutions out there. And in fact, some of our policy relies on us developing this solution in the future. There's a huge deal of, a lot of people in the natural resource management area are talking about carbon storage in soils and in our vegetation system. So soil carbon, you will hear a lot about that, because we have one of the major source of emissions has been soils and forests. Almost 30% of the anthropogenic CO2 out there is because of the degradation and deforestation activity on our land surface, and not just emitting fossil fuels. So that's so there are definitely some good solutions out there, but really we have to be wary of the bad ones.
Thank you.
Sure.
Yeah, thank you for your presentation. I was just thinking through the ratings and also some of those things you brought up this morning. And I just want to get your views about what climate scientists can do to simplify observations, climate observation and scenarios to the contributors of greenhouse gas emissions, so that we could have an appreciable impact with respect to mitigation and adaptation. I don't know whether you get my question?
Yeah, I guess what you're saying is how can we climate scientists reduce the uncertainty? Is that part of the question?
Yeah,
So
just
that-
basically to make the message of climate science more simpler to the contributors of greenhouse gas emissions, rather than all
Yeah.
these predictions and all of those figures, maps, and all of that.
Right.
Just to make sure, I mean, to the layman, to be able to, I mean, coordinate the thoughts of the projections.
Yeah, thanks for the question. So maybe it's a good idea to end on that note, answering on that point for me. And I think communication is the key here. And climate scientists agree that they've not done a good job in the past, but they're doing better and better. The other side of our opposing team, have done a better job with PR out there. But the system is complex, and we need to appreciate that, and that complexity will always play in. But we need to communicate that there needs to be more science education. Most people don't just understand greenhouse effect out there. So I think a basic training and education is needed. So that's a short answer, but thanks for that question. And I have to go to my next meeting now. So I really appreciate your time and attention.
Thank you.
Imtiaz, thank you.
Thank you.